start at the plot, the body plot of the system. So starting from the handouts you have, and allow me not to repeat the whole information. And so basically here from the information, and then we use the same strategy. We pick up the three values, and for our minor sketching of the thing here. So when omega equal to omega n, then here the magnitude. The face. This one can be derived from the equation there, and that will be pretty much is log and Q zeta. Okay, to arrive to this step won't be hard as long as you just plug it into the arrangements carefully, and you should be able to reach this one very quickly. Okay, and this one is 90 degrees. Okay. So again, we calculate is m. J omega when s equal to J. Okay. And then when omega is very small, then this one is almost 0, and this is almost 0 degrees, and omega is very large. Then this is about minus 4. So, sorry, here, let me take, I should take is this log. So this is minus 40, and this is minus 180 degrees. So with these things in mind, and then we can try to sketch is, say, if we pick zeta for any number here, we can try, and for magnitude, so to this end, to the left hand, omega is very small, so the magnitude is pretty much is like here. Okay. And then to when omega is very large, is the slope is minus 40. So here to, I would say, draw a asymptote is the slope is minus 40, and that's a dB. And again, this is the order unit is in decibel here. Okay. And so here we've been taking off this and this drawing. Okay, and for this one, say when omega equal to omega n, so that means at the resonance frequencies. Okay. So this magnitude is basically we can pick up any number and say zeta. We can pick up zeta equal to, say, from 0 to 1 or any number. And then basically that we have a peak here, okay? So for example, here we pick up any zeta and we can calculate the number here. We pick up the different value of the zeta, we have a different number here. So here we simply connect the whole curve and kind of put into this smooth one, and then basically that would be something like this. This is for the value of the zeta for certain values, and then here if we can have a different curve for different value of the zeta. So that basically will apply just like the handouts here, okay? And that one just like your vibrations here. So that depends on this curve. The peak will be depends on the curve, the zeta value. The same thing for angle. So for angle here, when omega is very small, that's starting from 0 here. So here that's 0 degrees. So when omega is very small, then the asymptote is 0 degrees. When omega is very big, then that is approaching to this is 90, and this is minus 180. So when omega is very large and that approaching to here, and at the corner frequency, at the resident frequencies, the value equal to 90 degrees. So that means here, right at the omega equal to omega n, the value equal to minus 90. So from here we can connect from the asymptotes, this curve must pass this point and then transit to the here smoothly. So that would be something like this. Okay. So that is for these systems, and this is a second order system, and that is very popular. So here I like to spend a little bit more time to categorize the second order systems from here what we have. Okay, so this is the Bode plot for these traditional second order systems. And here let me take a topic away from the Bode plot, and then let us to categorize the second order system again. And this might be related to, say, for example, the final exam or whatever, because that is second order system. Okay, so here let me review. This should be our last time to categorize, to revisit. Okay, so here we consider a transfer function, and let me rewrite this one again. I haven't started designing the final exam, but I can tell you the final exam pretty much cover the topics we exercise at the majority, the homework 6 or homework 7. Those are the topics being covered after test 2. But from here, the exercise, from doing the homework, you can see basically we kind of using the certain techniques back to the test 1, right? So the characterizations of the second order systems. From there, you design the design range, right? And how to define the design range, that means will depends on how the performance of the system will be. So those topic has been covered in homework 5, homework 6, 7, and that will be our final. So in this way, the one quick suggestions from here is, I would say final will be accumulative, okay? But with the majority of the skills will be focused on the 6 and 7 if we practice, yes.
Do we need to know the Laplace, inverse Laplace transformation?
I think the final, I can say, if you like to, I haven't think through, and the plus, probably no. Probably no.
I need to know if you have to put them on the cheat sheet or not.
If you would need the plus, I will write it on the board. How about this? Okay, so I will write on the board. So you don't need to prepare the plus on your cheat sheet.
Okay. In terms of the cheat sheet, Mason's rule.
Mason's rule, not
Okay.
And that is to derive the transfer functions. In transfer function, we have a couple ways to do it. And I know some of you prefer to go to the Mason's rule, and majority is go to traditional algebraic derivation from the block diagram. But I do know some of you like the Mason's rule. So it won't hurt, because who knows, I haven't started designing the exam products yet. So you can prepare that one. Mason's rule won't occupy too much space. Right? Once I have these things almost complete, I will give you more information, give you more hints about. And again, I will try if the native techniques from for the exam won't be go beyond too much away from the homework 6 and homework 7. Okay, so that is the I want to test, evaluate is your skills doing the controller design, and that is my intention. Okay, so for this one, the transfer function C over R, and here we define is our M of S, and this one is equal to this. And so here we can rewrite the whole things, and before we do the frequency domain, so here is our frequency domain analysis. So that means we introduce S equal to J omega. So that is the new thing. And earlier we have learned is from the time domain, and here we want to look at from the frequency domain. So that is a new thing. So we set up our analysis different from earlier. So here this will be equal to this. We plug in omega S equal to J omega, and then rearrange. I scale the both numerator denominator by this constant. So that basically will be equal to this. So here I arrange into real part and imaginary part here. So why not? And let me replace just like your let me replace a parameters here. So here I want to replace is let you defined by these parameters here. So that means here will be easier for our later writing. So basically U is a parameter of the frequency. So here we want to know is, so this one we define the function of the U. Okay. So here we have that kind of the dimensionless parameters that we can study. So the magnitude. By that one, that will be the magnitude of this. This is a complex number, and that is a parameter of the omega or u. So the scale, the magnitude will be the real part plus square the imaginary part square root depending on these things here. Okay. So. Phase. I just get the information prepared. The phase will be equal to the numerators minus the denominators here. So that will be equal to minus arctangent. Here zeta u and 1 minus u squared. Okay, with the two informations ready, then we can do a little bit parametric studies. So here we have this one. Actually, if you would take so, for example, if you would take the transform into the decibel scales, then basically this magnitude will give you this curve. So if you keep changing u, okay, and that means you keep changing omega, then you trace the point, actually you will get is this curve drawing. Okay? Okay, that's the first one. And the second one, in our schematic drawing, here we know the peak will be somehow somewhere nearby the resonance frequencies. And here we can use this equation, we can precisely calculate the peak and how to is the magnitude of the peak and where it occurs. So the second one is this. We simply take to find the peak of resonance. Then we can try is this. We take the derivative of the magnitude and respect to u with x equal to 0, then basically we're looking for the maximum value there. So from here, if we take up this equation, we do the derivative carefully, then basically that is, let me write one more time, u, and we take this one, 1 minus u squared. Okay, so from here you should be able to find out that u should be equal to, by definition, omega n, and that value is equal to 1 minus 2 zeta squared. Okay. So that is the value here. So the maximum value of the n will occur when u equal to this one, or the resonant frequency equal to this value. Okay, and so so that means the maximum, the peak of the m occur at omega equal to omega n times this one. So from the handout, if you look at the curve carefully, if you have a handout, I don't know how many of you still have a few pages handouts here. So if you didn't have that one, help yourself. Okay, so that's a handout I gave on Monday. If you got it, help yourself. Okay, so go to 10 here. So if you look at the curve carefully, and then you can see basically the maximum value or the peak happens is not exactly at the omega n here. Here I'm kind of misleading. If you look at the curve, for the different value of the zeta, the peak is offset a little bit. If you pay attention very carefully. Okay? So again, you look at our the precise equation here. The maximum value or peak occurred actually is equal to this one. So that means that happened equal to omega n times a certain number. So it's not at the resonance, at the the resonance not happen at the natural frequency, but natural frequency multiplies this number. And when zeta equal to when the whole thing equal to 1, when zeta equal to 0, then that will be at the natural frequency here. But for all the damping system, then that will a little bit offset. Okay, so that can be described by this one. Then here, let me say A. For B, we can observe is this, and for this peak, that means the curve will be something like here. Okay, that is called the peak here. And the peak phenomenon will occur when what happens? When this equation is satisfied. So the peak will occur when the square root of this one is always legible. So that means the peak phenomenon will occur when one minus 2 zeta squared is always positive to make the square root legible, right? If the 1 minus 2 zeta squared is less than 0, so basically that meaning this equation doesn't satisfy. So let me keep going on this one. So that means the zeta is less than 1 over 2 squared. As long as you have the damping ratio less than this number, then you should expect the peak phenomenon. if you have a damping ratio greater than this number, what happened? Then the value will be like this. This is the magnitude, and let me say whatever we can take the decibel or not. Basically, that is something they don't have an overshoot. They just starting from there, then will keep going down. Okay, there's a no peak phenomenon for those things. Okay. Okay, and this one I didn't say when we talk about in the time domain, because that one, for some reason, I forgot. Maybe my brain didn't link to there. But here, that's a one here. Okay. So when we have the peak, the PM, the PO, the peak overshoot, and that is range, from here we can get that clear from this. Okay. And for D, the peak of M, we can calculate is this. Basically here we calculate is when M we plug in the U. Let me use the information. So M is a function of this one. So this is a magnitude. When we plug in U equal to, we calculate it there. Okay? So here I want to calculate the peak. And that one, if we plug in the U equal to this number, and into here we like to calculate the peak magnitude. And that one should be equal to this. So that means for this one, if we have a peak phenomenon, then basically the peak is equal to this one. This one. Okay? So from this analysis, we can precisely know what is the magnitude, what is the height here, and then when it happens, precisely, we can know this precisely. Okay?